We can verify the presence of a major wartime aviation site on Ballale Island containing the wrecks and remains of 3 primary Japanese aircraft types: Mitsubishi G4M bombers, A6M Zero fighters, and Aichi D3A2. Val dive bombers were left around the airfield, dispersal bays, and jungle edges after the fighting in 1943. The operational objective is to document, interpret, and, where legally permitted, physically recover these stranded historical airframes before complete environmental destruction occurs. The primary constraint governing this objective is geographical isolation. Ballale Island lies more than 300 miles by air from Honiara on Guadalcanal, the nearest major regional infrastructure hub. This distance imposes severe logistical limitations on any recovery or survey operation. The long survival of these wrecks was shaped by a specific operational decision. In late 1943, after Allied forces landed at Torokina on Bougainville, Balale and other Japanese positions in the northern Solomons were increasingly bypassed rather than seized by direct ground assault. The airfield was still dangerous, but it was being neutralized from the air and sea. This decision established the foundational constraint of bypassed garrison preservation. Bypassing an island severs exterior supply lines. The garrison receives little replacement aviation fuel, few replacement parts, and limited engineering support. This isolation did not spare the aircraft from combat damage, but it did prevent the kind of immediate post-assault clearing that often follows a captured airfield. Instead of being bulldozed away to reopen the runway for advancing forces, many wrecks and airframe sections remained on site. Without the ability to launch or repair every machine, the Japanese garrison left damaged aircraft exposed around the field. The airfield was neutralized by repeated Allied bombing, fighter sweeps, strafing runs, and naval bombardment. Ground crews abandoned crippled fighters and bombers in and around their dispersal positions, while aircraft still capable of flight could be withdrawn to the north. This sequence of constraints and operational decisions created a highly specific evidence signature. The dispersal bay geometry forms a structural map of the 1943 airfield. Unlike a dynamic aviation crash site where kinetic impact forces distribute debris across an unpredictable path, the Balale site preserves traces of a deliberate and engineered wartime layout. The distance between stranded aircraft and revetments reflects a deliberate wartime effort to disperse valuable machines against air attack. The orientation of the airframes points toward taxiways that have since been partly reclaimed by dense vegetation. This spatial relationship constitutes the archaeological context of the site. The position of each bomber and fighter tells a forensic story regarding the final operational days and defensive posture of the isolated airfield. The entire island functions as a single macro artifact. Moving any individual airframe from its original bay would not merely relocate metal, it would sever the location, heading, and orientation that make the wreck part of the original defensive grid. After the war, the absence of a large occupation force meant no immediate runway clearing operation stripped every wreck from the field. The island's remoteness, lack of permanent settlement, and the landowner's later refusal to allow large-scale scrapping also limited early industrial salvage. The layout survived, but not in a stable condition. Tropical canopy rapidly engulfed the dispersal bays and trapped moisture around the airframes. The gap between 1943 and modern rediscovery is defined by this continuous exposure. The environment systematically weakens the stranded aircraft. Recovery planners therefore face a procedural contradiction. The airfield geometry can still be read, but the metal preserving that geometry is failing. Any intervention must therefore be planned around a site that cannot accept ordinary roads, cranes, or supply chains. Dense tropical growth threads through control surfaces, ribs, and engine mounts, reducing load-bearing strength each wet season. The fleet cannot remain in place indefinitely, yet ordinary extraction equipment cannot reach it without creating new damage. The question becomes how to retrieve a fragile airframe after the jungle has sealed the exit. The surface geometry of Ballale Island presents a hard limit on any recovery operation. The spatial problem extends far beyond the dense vegetation surrounding the dispersal bays. The island is associated with the deaths of 517 British prisoners of war brought from Singapore to build the heavy bomber runway and surrounding defensive infrastructure. Post-war investigations recovered and reinterred hundreds of bodies. but the exact locations of all burials and killing sites were never fully resolved. This historical reality fundamentally dictates what can and cannot be done on the island. Japanese forces used these prisoners for airfield construction, and in 1943 the surviving prisoners were executed after the airfield was operational, and invasion fears increased. This creates a severe ethical, archaeological, and permitting constraint across the island. Unmapped or uncertain burial areas impose strict boundaries on ground disturbance. Heavy machinery near the airfield, jungle paths, or suspected grave areas would require documented approval, careful survey, and extreme restraint. Tracked excavators, heavy mobile cranes, and commercial land clearing bulldozers cannot be treated as routine tools on this terrain. Recovery teams cannot simply grade the ground or cut wide operational corridors through the brush to reach the stranded aircraft. Surveyors and engineers must navigate the island with minimal disturbance, taking care not to disturb the topsoil where grave evidence may survive. This terrain limit blocks most standard heavy lift methods from accessing the site. Within that restricted footprint, the aircraft material keeps degrading from every exposed edge. The aircraft are constructed primarily from wartime aluminum alloys, including duralumin-type materials in vulnerable structural members. Duralumin is an early aerospace alloy family blending aluminum with copper and other elements to achieve high tensile strength at a very low overall weight. However, continuous exposure to high humidity can turn the surface of the aircraft into a persistent electrolyte. This moisture can initiate pitting, exfoliation, and intergranular corrosion in vulnerable sections of the airframe. The chemical attack often focuses on microscopic grain boundaries and on areas where dissimilar metals meet. The trapped moisture acts as a galvanic cell, chemically weakening joints, skins, and fittings from the inside out. The daily thermal cycles of the island accelerate this damage. High ambient temperatures during the day expand metal joints, allowing continuous tropical rainfall to seep deeper into the structure. As the air cools at night, the joints contract, trapping moisture deep inside wing spars and fuselage bulkheads. Because this degradation may occur internally at the microscopic level, exterior aluminum skins can appear more intact than they really are. However, the internal structural strength may be badly compromised. The metal can become embrittled. Components that once managed violent dynamic flight loads may no longer tolerate twisting, dragging, or uneven lifting. The loss mechanics of this bypassed fleet are defined by this slow structural failure rather than sudden kinetic impact. A traditional crash destroys an aircraft in seconds through massive deceleration loads. On Ballale Island, the destruction is chemical and relentless. The initial disabling of the fleet during the early strafing runs played a crucial role in this decay. Bullet holes and shrapnel tears punctured the protective outer paint and factory anodized coatings. These breaches provided immediate entry points for the tropical moisture to reach the unprotected internal framework. These compounding factors create the extraction bottleneck. The airframes need broad, even support from below, but the restricted terrain prevents routine crane access. In remote salvage work, the fallback would usually be dragging or winching. Here, severe intergranular corrosion removes that option. A heavily corroded wing would not pull as a unit. Its ribs would collapse and steel cables would cut through the embrittled duralumin. The physical evidence is therefore locked inside a narrowing engineering window. Each wet season weakens the load paths, while the permitted access footprint remains minimal. How could engineers physically move a decaying bomber out of the jungle? Visual surveys of the Balale site in 1968 suggested the presence of highly intact aircraft. However, physical inspection revealed a contradictory reality on the ground. Some airframes had been stripped of usable parts by Japanese personnel during the war, and others were later disturbed by visitors and scavengers over decades. The target aircraft was an Aichi D-3A2 Val dive bomber, later identified as manufacturer number 3178, one of the rarest surviving examples of its type. From a distance, its wings and fuselage appeared to form a complete, structurally sound shape. Up close, much of the aircraft was a fragile shell locked together by damage, corrosion, and tropical overgrowth. In 1968, aviation restorer Robert D. Merritt launched a targeted recovery operation to identify and extract selected A6M Zeros and Aichi Val airframes from dozens of wrecks hidden beneath dense vegetation. Once the Val's identity was confirmed, it became the extraction target. Having established the target, the recovery team transitioned to structural assessment. They had to determine if the airframe could survive the physical forces of extraction. The corrosion present in the airframe meant that lifting it as a single piece could result in catastrophic structural failure. The engineering decision was straightforward but procedurally difficult. The team determined they must cut the damaged airframes into manageable sections to reduce twisting loads and prevent the brittle aluminum structure from breaking apart. Before they could execute any cuts, they had to understand exactly how the aircraft was currently holding itself together. The immediate problem was not corrosion as chemistry, but corrosion as seizure. Steel bolts passing through aluminum spars had locked nuts, ribs, and fittings into place, turning factory separation points into unreliable obstacles. A maintenance-style teardown was therefore unsafe. High torque on frozen bolts could tear the surrounding embrittled aluminum and send fractures across primary load-bearing structure. The team had to adopt a destructive disassembly plan to save as much aircraft geometry as possible. To separate the wings from the fuselage without causing uncontrolled structural collapse, they had to bypass many original attachment points. They chose practical cut lines across the wings and fuselage where hand tools could reach thin aluminum without erasing the aircraft's recognizable form. Each section had to be small enough to carry, but coherent enough to preserve alignment references for a later rebuild. The cuts sacrificed original load paths to keep the historical geometry intelligible. The assessment phase narrowed the problem to one question: how do you separate wings that behave less like bolted assemblies than a single corroded shell? The next constraint was movement, and the answer was to abandon large-scale lifting. An intact bomber wing could not negotiate a narrow, weaving jungle trail without snagging on timber and root systems. Sectioning the wing panels and fuselage reduced both the physical dimensions and the static weight of each load. The team utilized basic hand tools, including hacksaws and pliers, to physically cut through aircraft skin and internal ribs. Once the airframe was fully sectioned, the logistics shifted from machinery to pure human labor. The dense vegetation required an extraction footprint no wider than a single footpath. Local laborers hand-carried the severed aircraft sections through freshly cut jungle trails. This slow and methodical process established a distinct method fingerprint for the entire operation. Each piece of the dive bomber, from the vertical stabilizer to the severed wing roots, was manually navigated through the high humidity of the tropical forest to the shoreline. The carrying mechanics demanded strict physical discipline. A severed wing section, even stripped of its heavy engine and mechanical systems, remains an awkward and unbalanced load. The laborers had to distribute the weight across multiple carrying points. On the narrowest stretches, carriers advanced in staggered positions rather than side by side, using careful footing to limit flexing, twisting, and cracking under dynamic loads. At the coast, the team transferred the airframe sections onto a waiting coastal barge. The shoreline transfer continued the low mechanization logic of the jungle carry. The shallow draft vessel pulled directly up to the shoreline and accepted the individual aircraft sections directly from the carrying teams. The barge then securely stowed the dismantled bomber and initiated the transport phase across the ocean to the nearest major logistical hub in Port Moresby. Upon reaching Port Moresby, the extraction choreography escalated from slow maritime transit to heavy airlift capabilities. The manually sectioned pieces were loaded into the cargo hold of an RCAFC-130 Hercules transport aircraft. Only the sectioned format allowed the pieces to fit inside that hold. The Hercules then transported the salvaged aluminum structure to Canada, where it would eventually undergo a long and difficult restoration history. The method set a precedent. Recovery could remain small, slow, and low impact, but future teams would have to decide whether that restraint was a model or an obstacle. In 2007, a specific operational window opened that permanently altered the Balale site. A disputed salvage effort secured government permissions to remove multiple Japanese airframes and major components from Balale and nearby islands. Contemporary accounts and later legal commentary do not support a single, uncontested figure of exactly 11 intact aircraft. The operation still marked the definitive end of the island's protective isolation. The work shifted from localized recovery to larger-scale commercial salvage. This time, the central problem shifted from simply reaching Balale to controlling what could legally leave it. Extracting this quantity of material immediately triggered complex legal friction. Historical military hardware could not move on physical access alone. It required a documented chain of custody, valid export authority, and customs clearance. The dispute drew in Solomon Islands law, customary land interests, museum claims, ownership questions, permits, and the larger question of whether the wrecks were abandoned relics, commercial salvage, or protected heritage. Those interests did not always align, making legal authority the controlling constraint rather than the extraction route. As the salvage work proceeded, the damage shifted from possible to measurable. The loss was practical. Once aircraft were disconnected from their dispersal bays, the original alignments could no longer function as evidence in the same way. Empty bays could still retain scattered support equipment, coral sand, jungle paths, trenches, and blast walls. But without the aircraft as anchor points, those surviving features became harder to interpret. Future surveys could still read parts of the defensive grid, yet major sections of the 1943 operational layout had been stripped of their central artifacts. That trade-off became the central argument in the ensuing legal battles. Conservationists prioritized the site record left in place, while salvage operators argued that jungle exposure guaranteed the airframe's destruction. In practice, the operation favored preservation of the metal over preservation of the dispersal geometry. Once export documentation cleared the target material and major components left the dispersal bays, the result was irreversible. Bays that had once held the island's ghost fleet were left as shallow depressions in coral sand. The unified historical location no longer existed in the same form, but legal permission and physical extraction solved only the first salvage problem. What happens to an airframe when it is abruptly pulled from a stabilized 7-decade microclimate? By 2018, the last major intact wrecks reported on Balale were being disassembled and moved toward the beach, including 2 Mitsubishi G4M1 bombers, the rear fuselage of another G4M, and other major components. The salvage team relied on established permission and export frameworks to clear the material for transport. This legal maneuver transferred the physical assets, but it initiated a massive conservation challenge. The aircraft were no longer threatened by dense root systems or tropical canopy moisture. Instead, they faced a new corrosion risk caused by removal from the environment in which they had decayed for decades. Extraction immediately altered the balance of moisture, salts, dirt, temperature, drainage, and surviving coatings that had governed each airframe for decades. Pulling saturated metal out from under the canopy exposed damp aluminum alloys to new cycles of sunlight, airflow, drying, salt concentration, and oxygen. As trapped moisture evaporates, corrosive salts and contamination can remain inside joints, seams, and porous corrosion products. Under uncontrolled humidity, those salts can keep drawing moisture back into joints and seams, allowing active corrosion to continue even after recovery. If left untreated, a recovered airframe can continue to deteriorate rapidly in storage or on a transport dock. The new environment does not magically save the aircraft. It creates a different corrosion problem. Museum conservation teams face a difficult timeline upon receiving these extracted airframes. They cannot simply place rare aircraft into ordinary storage and expect them to survive. The extraction forces an immediate requirement for assessment and stabilization. Conservation engineers must inspect accessible components, identify alloys where possible, evaluate salts and corrosion products, and decide which areas can be cleaned, desalinated, coated, supported, or left undisturbed. Treatment may include mechanical cleaning, careful washing where appropriate, corrosion inhibitors, protective coatings, controlled relative humidity, and custom internal supports. The procedure is not one universal chemical bath. It is a case-by-case stabilization plan shaped by the metal, the contamination, and the intended display. Following stabilization, conservation teams can spend thousands of man-hours reinforcing crumbling wing roots, skins, and joints with custom-fabricated supports. These hidden supports carry display loads, allowing original historical skins to survive without bearing active structural weight. After the 2018 removals, the central operational base that once held dozens of military aircraft consisted largely of empty earthworks, shallow depressions, overgrown blast walls, memorial sites, and scattered remnants. The island landscape still provides forensic data. Airfield traces, trenches, graves, surviving debris, and smaller fragments that non-invasive survey may still locate. But the original airframe positions can no longer verify every aircraft variant or the exact operational density of the ghost fleet. The aircraft that survived recovery now reside in specialized aviation museums and private restoration facilities worldwide. They exist primarily as preserved aerospace hardware, structurally stabilized but disconnected from their original deployment coordinates. The recoveries saved extremely rare material from environmental destruction, but future fieldwork now depends on empty bays, residual fragments, and non-invasive survey. The final question is whether those methods can locate the last buried evidence before the jungle and corrosion erase it.